Hey everyone, in this video I want to do a deep dive into Azure SQL Hyperscale. And I'm actually going to kick off with something I never normally do, which is to give my opinion on something. And the opinion is the name Hyperscale is terrible. It definitely conveys the idea that it's super useful when I have these very high capacity, very high performance requirements. But for me, it makes me think that I would only use it when I have these huge capacity or huge performance requirements. And that really isn't the case, which we're going to explore through this video. And also, as we'll see as we go through this video, as I've learned more about it, it actually seems like Azure SQL Hyperscale is the right option in many Azure-based database requirements. And you can draw your own conclusions. So I want to kick off with reset your mind and don't think that, oh, Azure SQL Hyperscale, I only care about that when I have these massive performance or massive capacity requirements. Now, normally, if I think about Azure SQL Database, we have a server. So I can think about, okay, I've got my server. And there are various elements to that. And obviously, we know we have our SQL server.exe process. That's the main, really brain of Azure SQL Database. And then within that, we have the compute processes. We have a certain amount of memory, which we can use for our buffer pool. We have our tempDB. And then we have our transactional logs. Which is super important for durably storing the transactions that come in before we want to acknowledge them to that calling application. And then we can think about durably storing them in the actual data files. And there's obviously many other different components those go into my all-up SQL Server. But typically, we have all of these things in the same box. Now, the storage could be remote. On premises, we might use a very powerful storage area network, for example, so we can really push those amounts of capacity, the amount of performance we can do those things. But that doesn't translate well when we think about going into the cloud. Hence, Azure SQL Hyperscale. And the big thing we have here with Azure SQL Hyperscale is, well, firstly, it starts to separate the things out. So if we had all those different components, let's wipe that away and think about Azure SQL Hyperscale. So I can think about the compute, the log service, and the storage engine, i.e. the pages we have of our database. And again, I have to be able to separate them out if I want to be able to achieve very high performance, very high capacities, potentially, because I can't just stick it all in one box. So I can think of, well, I still have my compute. And that would still have things like my tempDB within there. And that would be my primary compute. And I would have my read-write sort of talking into that thing. And then the first thing that gets separated out is the idea of the transaction logs. So now we have a separate log service. Now, I don't have to think about this. It's just there. It's been done for me. But there was actually a massive amount of work that went into this log service, because if we think about what is required for the transaction logs, this is where it has to be durably stored. It has to be stored with data integrity, but it has to be able to keep up with the performance of the transactions coming in, or it would impact how the database functions. So I need super strong data integrity guarantees. I have to be able to keep up with whatever is being sent to it. And also, there's going to be other things potentially wanting data from it. Secondaries, replicas, the actual long-term storage. And so a massive amount of engineering went into Xlog. So this is a new service that enabled us to separate out the transaction logs from the primary compute. And so I don't have to think about it at all, but it's designed such that it can have very low latency. it has very high throughput, and it's going to durably store these with very high data integrity. So I can think about, well, hey, from the compute perspective, when this primary gets these transactions coming in, what it's going to go and do is send it to this log service, which again, we don't actually have to think about, it's just there, but realize there was a lot of work went into separating out the logs from the actual compute and then that durable storage. Speaking of the durable storage and thinking of that storage aspect, how do we actually durably store our database? Because we used to have those data files. And so what they've done here is they've created page servers that will offer up pages of the database. And the way this actually functions is they're in pairs. So what I'm going to get is a pair of the page servers. So these are my page servers. And you can think of it as a cache. Now, once again, it's always a pair, and they are operating in an active mode. So they're both doing things. Now, think of these as virtual machines in Azure. And if it's that little D variant of a virtual machine, it means it has locally attached temporary storage that it's using storage from the host that's running the VM. So it's very high performant, super low latency, very high performance. In fact, with these, it's an NVMe. So it has this NVMe temporary storage, which it's using along with the memory to power the cache. So if I think of layers of what's going on, this is kind of my compute up here. Well, this is a caching technology. And then to back that up behind the scenes, what it's actually then going to use is Blob. Good old Blob. And of course, with Blob, it means there's always minimum 3 copies. Now, if I'm doing zone redundant, then those 3 copies would be spread over the 3 availability zones in that region. Additionally, I can set these up as zone redundant as well, the whole configuration. I think today I can do it through CLI and PowerShell and templates. I don't think the portal shows me that zone redundant option today, but absolutely I can do that. And I can think about, so this is that really durable storage. So if that's a caching layer, this is durable. And based on the sizing, and we're going to go into detail about this cache can store a copy of everything that's actually in this blob. Now, when I think about my database, my sizing of the database can actually be between 10 gigabytes all the way up to 100 terabytes. Now, that's at current time. Things can change. You should actually go and check the documentation for what the maximums are based on today. But it can be as small as 10 gigabytes. It doesn't have to be these multi-terabyte databases, which starts to give you a hint about, hyperscale, well, maybe I can use it for more ordinary circumstances. And there's no pre-provisioning. I don't tell it the size of the database. I just write data to it, and it just automatically grows. So I don't have to think about it as the customer. All I think about is, hey, I create it. I'm going to give it a certain amount of compute, which we're going to see. I don't tell it anything about the storage. It's just going to grow these automatically for me. And what it's actually doing behind the scenes is if I think about these pairs of page servers and these blobs, what it does is it creates sets of these for every 128 gigabytes. Now, it's going to auto grow in 10 gigabyte increments. So this auto grow is in 10 gigabyte chunks. As I'm growing, it will go and add more sets. So these pairs of page servers, hey, as I start to breach, getting close to that 128 gigabyte, well, it will go and add additional sets of page servers. So it's sharding my database, it's separating it up into different blob files, into different sets of page servers. And so by sticking to this 128 gigabytes, well, it means the cache size for the page servers is always big enough to have a full copy of whatever is in that blob. And that's really a key point here. So when I think about this cache right here, they actually developed a new type of resilient buffer pool extension. So this is actually an RBPEX cache. And it's what's known as a covering cache, i.e. it's guaranteed to have a full copy of everything that's in that database. And that's important when I think about performance. So yes, the blob is my very durable, huge numbers of nines for never losing data, 3 copies of it distributed however I want it to be. It's also super useful because in here I can do things like snapshots. And that's really useful when I think about taking my backup, doing my restores very, very quickly, but it's not very high performant. So the key point here is these page servers, they cache everything that's in that blob. Again, these pair of servers in that local NVMe in its memory, by restricting it to 128, there's always enough NVMe to cache everything that's in that blob. And that's part of the story when I think about the really high performance we're going to get. And of course, remember, the compute is sending the transactions to the log service. And then what actually happens is the logs then find themselves into all of the page servers. The page servers actually pull the page blocks. So the log service doesn't have to worry about how many replicas there are. People pull from the log service. Again, a whole new set of architecture created specifically for the cloud. Now, these never stop and start, but obviously things could happen, things could fail. Maybe I go and spin up a Geo-replica. And so if ever they have to be rebuilt, they will seed themselves from the blob storage and populate that RBPEX cache from a full copy of the blob. So that gives you some hint about how it starts to enable this really high capacity, because again, it's just going to scale out these pairs. And again, I don't care. I'm just writing data, and it grows in those 10 gigabyte increments, and it adds the pairs of page servers as it needs to. Nothing I ever worry about. And we have this nice cache to make it very high performant. So then on the compute side, what is it I worry about? What is my responsibility? Well, just like a traditional database, it's a relational database. We have a primary. So our primary is that read-write connection from our application. Our intent would be read-write. We're going to have to talk to the primary. It's the only one that can make writes into our database. And we specify the compute performance we want. Now, there are different models and options available. I'm actually going to start with the idea of standalone. So if I have standalone, so the default, and we are going to have 2 options here, but it's going to be provisioned. And as the name provision suggests you, I'm just going to tell it, hey, I want X number of vCores. There is no DTU model when I'm dealing with hyperscale. It's vCores. And obviously, I'm going to pay for these. So the whole point here is, what do I pay for? Well, I'm going to pay for the number of vCores. And obviously, I'm going to pay for the size of my database. They're all cost elements I have. And we can see this. So if I jump over for a second, so if I'm creating a brand new SQL database, now, this is the page just opened without me changing anything. Notice it's even giving me a little, hey, SQL database hyperscale, low price, high scalability, and best feature set. It's kind of calling it out there just on the generic basic, hey, I want to create a SQL database. There's nothing hyperscale specific yet. And if I go and look down for my compute and storage, it's actually picked hyperscale as the default, which is kind of weird because I was like, well, this is only for very high performance, very high capacity. If I do configure, so again, it's selecting hyperscale here, but I could go and change its general purpose, business critical, etc. And again, it's the vCore model only. I'm doing provisioned, and you obviously can see it's giving me what my other option is going to be. All I configure is the number of vCores. Now, this is giving me up to 80. If I change my configuration, you can see, well, there's actually a premium series and a confidential computing series, and those give you different numbers of potential max cores. So the premium actually would let me go to 128. So you can see the difference and how the memory would be allocated. So there's different options here. But I'm not specifying any concept of amount of storage. All I specify is the amount of vCores I want. That's my only configuration. So hopefully this starts to emphasize the idea that when I think about the compute and then I think about the storage, they have complete independence. There is no correlation between what I can allocate for the compute and what is available in terms of the actual scale of the database. I just configure the compute I want based on the data I import in or create within the database. This is just going to grow potentially up to, at time of recording, that 100 terabytes, but it can be as low as that first 10 gigabyte increment, which is how it grows. Now, I mentioned this covering cache. So this cache in the page servers completely covers whatever is in the blob because it's these 128 gigabyte increments, so it can always be big enough. Now, there's actually also a cache in here. It also has a RBPEX cache. However, it's non-covering. There's no way this cache can be big enough to potentially cover 100 terabytes. So this is your more traditional type cache for the most recent, the most used pages that is seeing going on within the SQL database. So that's a more traditional, but it gives you the idea that I have two layers of cache going on here. So where it can meet the requirements from the local cache actually within the compute layer. If it doesn't get a hit there, well, then obviously it goes and talks down to the page servers where it serves it from its very high performant cache. And again, it's resilient, so it would survive basic reboots, but if these completely fail, it will just reseed it from the blob. And that's what drives a lot of the performance of the hyperscale, where we have these multiple layers of cache. Now, obviously, I'm specifying X number of vCores when I actually go and create my database. But I can change it on a running database. I could increase this number of vCores. I could decrease the number of vCores. And what it actually does behind the scenes is, based on my new configuration, my new service level objective that I'm specifying, number of vCores, the type of SKU, it will create a new instance. That new instance will take a couple of minutes to create. It will wait for it to be ready. It will then switch new connections to go to the new instance. Because remember, there's nothing actually stateful, really, that I care about in the compute layer. Where is the state? The state is in my log service, xlog, that's the transactions that are potentially not being durably stored to the page servers, and then the blob. Even the page servers don't really have a state that I cannot lose. The state is in the blob and in the log service. So I can replace these pretty easily. So I go and create the new one of the new size, wait for it to be ready, switch the listener to now go and point new connections over to here. And then for existing connections, hopefully there might be a couple of second interruption, but that should be handled transparently by the application retry that you build into your application. And so that's how I can change these dynamically, because it's just going to go and build a new one based on the new service level objective, the number of cores, the type that I specify as part of my configuration. Now, obviously, that does mean you could automate that. You could absolutely say, hey, I know at night, based on the type of server this is, doesn't get used very much. So I could write an automation to 8 p.m. Let's reduce the number of cores. Then at 7 a.m., spin it back up again. Maybe I have some monthly batch that uses more and I don't have read replicas, which we're going to talk about, I could adjust this. Now, the way it works is it's billed hourly on the maximum number of CPUs. So there would be no point in every few minutes changing it. You wouldn't get any benefit from that. But certainly, potentially, key seasonalities of the day or even week or month, you could automate some changing of the numbers to, based on busy times and quiet times, change number of cores so you could optimize your billing. And of course, as long as the application handles retry correctly, there'll be a tiny, tiny blip in what's going on. Now, I mentioned provisioned was one of the options, and we saw it on the screen as well. In fact, if we jump over quickly, we see this nice second option of serverless. And I just mentioned, well, you could use automation to scale it up or down, or you could say serverless. And now what we see is maximum and minimum numbers. And we can actually see the minimum number is 2, and it's half a vCore. Now, the normal ratio is, I think it's actually 8:1. So as I scale up, yeah, you can see it starts to change. So at 8, maximum, the minimum is 1. And so it will start changing. I don't set the minimum number, I just set the maximum. And that's kind of the ratio, that 8:1, until it gets below 8. At 2, the minimum is half, is what I can have. Now, I don't have all the same options. I'm just using the standard series when I'm doing serverless. But now it will just automatically change the number of cores that is being exposed to my database based on what it needs. So it's going to optimize my spend. Now, obviously, it means I'm going to pay more. So when I use the serverless option, one of the things it's obviously going to do now is, yes, I have serverless. Now I'm specifying, really what I'm specifying is the number of max. So I'm specifying, hey, the maximum number of vCores. And then for that ratio of kind of 8:1, it's also going to set the minimum number. And then I'm only going to pay for the amount it needs. You can almost think of it as sort of masking and unmasking. So you're not going to get this 2-minute thing every time it's scaling. It's using a different method. But I'll pay for the amount of CPUs it requires based on the work it's doing at that moment in time. And so, yes, it's costing me more money per vCore in this mode. I'm spending more. But if I have these big variances in the amount of compute I require over a period of time, overall, it will save me money. So I would need to understand what is my usage pattern of the compute. But if I get these big peaks and these very low lows, well, then this might be a better option for me. So it's something you'd want to look at and understand what's the best price optimal option for me. But that's available there. Now, another thing we saw was we had that idea of HA replicas. You might have seen that in the screen. If we jump over to that again, and we go back to provisioned for simplicity, it's got this idea of high availability secondary replicas. And I have this little slider from 0 up to 4. So 4 is the maximum number. And it's been very specific in its naming. It's high availability replicas. Because this could be a super important database. It's still a relational database. So I have one primary. That's all I can have. But I want the ability to be resilient from a failure. Things can happen. And it could be a failure, and I don't want to wait for SQL to rebuild a new one and maybe have that few-minute outage. So what I can do is I can, as you just saw, I can have between 0 and 4 high availability replicas. Now, obviously, if this is read-write, these are going to be read-only. And you notice there wasn't a option for configuration of the hardware. These are a clone. So these are clones in terms of the configuration of the primary. Same number of vCores, the same provisioned or serverless. Whatever this is, these will be as well. And of course, these can be spread over AZs if I'm in a region with availability zones and I pick the zone redundant option. They do not have their own copy of the page servers. This, again, is one of the benefits of separating out the compute from the storage and the log service. They're using the same page servers as the primary. I'm just basically scaling out the compute. So I'm adding resiliency. It will automatically fail over if there was a problem here. There's no need to change connection string. I can, as an application, set my application intent to be read only. And then if they're available, it would redirect my application to one of these HA replicas. But they are using the same page servers. So what does that mean? Give myself a bit more space up here. I'm going to move you up, 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 up. What it means is, from an Azure perspective and from my architecture, these have to be a different color in the same region. So all of this is in region 1. Yes, they can span availability zones, but they cannot span the region. These page servers live in the region. The compute has to talk to page servers in the same region, or latency would be terrible. So this all is existing within a single region. So this gives me high availability, very fast failover. It gives me the ability for things that just need read access. They can go and talk to these instead of this from the compute perspective. And I talked about the page servers kind of pull the page blocks from the log service. These are pulling from the log service as well. So this is how these get populated with various things as well. Those go and pull from it. Again, log service isn't pushing because then it would have to be aware of them all. These things just go and pull from Xlog. So this is how I can get nice resiliency. But maybe I want more than that. Maybe I have a ton of analytical workloads and I want to be able to go and talk to particular sets of read-only servers. Well, I can do that as well. So one of the things I can actually go and set up, let's pick another color again, is I can set up named replicas. So now I can set up named replicas, which, as the name suggests, has its own name. So the application would now connect to a distinct connection string for this particular named replica. And the named replicas I can have between 0 and 30. I can have lots and lots of these. And what's interesting about the named replicas, they are not clones of this configuration. So they actually can have their own configuration. So for example, my primary, and if it has any replicas, might be provisioned with 40 vCores. Named replica 1 maybe uses Serverless with 8 max vCores. Named replica 2, maybe it uses provisioned with 4 vCores. So each named replica has its own configuration and its own connection string so they can be used. Also, these can also have their own high availability replicas. So, fun bit of math trivia. What's the maximum number then of compute instances I could have for a single hyperscale database? I'll let you think on that. It's 155, because I could have 5 here and then 30 of potentially 5 here as well. So that would be 150 plus 5, 155 max. I don't think you'd ever do that. The SQL team have done it to prove it works, but it gives you an idea of the potential. It's not just storage scale. It's not just how much capacity I can have and performance I can have. Actually, from a things consuming this, it's a crazy amount of compute I could throw at this as well for different analytical workloads, talking to different named replicas or apps or whatever that might be. I have a lot of power in that scale of, yes, storage, but also the compute interactions. But I'm actually lying to you because, and one of the concerns you've probably got right now is this is all in region 1. this is a super important database, got all this fantastic page servers and all these great things. It's in one region. And we always talk about we don't like the idea of ever having something in one region. So what I want is something in region 2. So let's have the idea of a region 2. And it doesn't matter what region I'm doing here. I'm going to go and pick this. And what I'm now going to do over here is create another instance. So over here, I go and create another SQL Hyperscale. And what this is going to be is a replica, because what I'm going to go ahead and create between these is a failover group. Now, this used to be called an auto failover group, and it may still say that in the documentation in places, but the name auto was terrible because basically it would never automatically fail over. It would fail over only if the entire region was down, which has never, ever happened. So the word auto has been taken out of it. And now I would want to use a customer managed failover policy so I control when I want it to fail over. And so what's going to happen here is that, hey, it's going to have its own set of all these components. It's going to have its own log service. Because it's another region, it's going to have its own sets of page servers in the same pairs, going to its own set of blob, talking to all of these different things. Once again, this could have 0 to 4 HA replicas. Actually, you could have named here as well, which could be your 0 to 30, which again could have the 0 to 4 HA. You could have another 155 over here potentially, so I guess 310 is actually your maximum number. But what it's going to do here is when you go and configure this, the first thing it will do is initially kind of seed it from the blob. And then what will happen is the log service for the ongoing replication will just start forwarding it. So it's going to forward the transactions. This is the ongoing, keeping that geo-replica in sync. So I've added this as a geo-replica up here. And then when these get forwards, it will replay. So they go to here, which will go to here. And that's how I now have this geo-replica. Now I can only have this in one additional region. I cannot add a geo-replica of a geo-replica. So today at time of recording, I have my primary region with all of its sets of infrastructure. I can add a geo-replica to another region, and I have that whole set of infrastructure over there as well. But I cannot chain geo-replicas. So I couldn't have a region 3, which is a replica of this one, or trying to add a replica of that one. So today it's a pair as part of that resiliency story. Okay, so hopefully that gives you some idea of its capabilities. But there's one more piece to this that I wanted to talk about. So far, we hinted about it over here. It was standalone. It's a single database that I'm configuring this provision compute for, or this serverless, so it's going to scale out. And it has this whole set of infrastructure. But it could be, as an organization, I have multiple databases, and maybe their peaks and their lows are at different times. And so what would actually be nicer for me is to have a set of compute capacity that I could share over multiple databases, and I would place those multiple databases together so they complement each other. So as one is having its peak, another one's got its low. When this is peaking, this one's low. So I'm going to overall get a better usage of my actual compute. Because remember, the serverless is more expensive. And so if I could co-locate databases but get a higher overall utilization of the compute, well, this would be a really nice option. And so enter in the idea of the elastic pool. Now, with the elastic pool today, it can be up to 25 databases in a specific elastic pool. So that's the maximum I can do. It is all provisioned. So it's X number of vCores. There is no serverless option when I'm using elastic pool. Now, the architecture of this is interesting. Not something you have to really know, but I'm just going to walk through it. So from an architecture perspective, and the reason I drew it as a different picture is everything is super similar. So I still have my primary, which is the read-write intent. So this is kind of the read-write option. Has my compute, my temp DB, etc., etc. But this is where I'm actually going to have, for example, database 1. And I'm going to have database 2. And I'm going to have, you probably get the idea, I probably don't need to continue with the examples, database C. I'm not going to really do that. Database 3. So now I have this idea of multiple databases that are coexisting. Now they're isolated. They are completely isolated still from a security perspective. They're just sharing a certain amount of compute for them. And I've done the analysis such that, well, actually, I know these three are going to complement each other very, very well. Now, they still have the same log service over here. You can still have the concept of the replicas and all of the other things. All of that still applies. But the page servers, well, actually, let's draw this a different color. What we'll actually end up with here is different sets of page servers. So we'll have page servers, and we have, again, the pair with its blob in the 128 gig chunks for DB1. DB2, well, it will have its own sets of page servers with its own blob. And DB3, yeah, it's going to be exactly the same thing. Now, again, you never worry about the page servers. I'm drawing it just so you understand that there is still, that's really the big separation of where it's doing this. So the log server is separating out the way it writes to these different sets, where it's bringing the pages up from. You don't need to know it. Remember, you never care about the page servers. You never set the page servers. You don't set numbers. You just write your data in those 10 gigabyte increments. The same thing is happening here. It would scale them accordingly. But that is the separation in this architecture. And one of the reasons for that is that I can bring databases in and out. So I could bring a database in. I could take it out of the elastic pool. And so obviously one of the nice things here is the page servers are separate. It makes it that much simpler to just go and attach different compute to my sets of page servers to enable me to do that. Now, although this is provisioned only, and it's X number of vCores, I can actually set a minimum and maximum on each database. So I could absolutely say on each one, a min and max number of vCores. And where this can be useful is if you think about things like a noisy neighbor. So I might say, hey, I've got 40 vCores. You're only allowed to use 10. You're only allowed to use 6. You have no limit. You can use whatever you want. And where the maximum is kind of obvious, and I can over-provision that number. So as long as they're not in time of contention, everything's great. If there is a time of contention, they're just going to get equal slices of pages. But the minimum I can really think of is super useful as a minimum quality of service. Because I could say you always get a quarter of a vCore. You always get one vCore. So in the time of absolutely worst contention, I've put them together terribly. They're not complementing each other. They're fighting for the resource. If I set these minimum numbers, I'm guaranteeing a certain amount of compute capacity. And for the maximum, remember, I can over provision. The minimum, there is no over provision. i.e. these minimum numbers cannot add up to more than the total number of actually allocated, because it's a guarantee. You're always going to get this amount in times of the worst possible contention. And again, outside of these minimums, if they do suddenly just start competing, they're just going to get an equal number of pages. They're going to separate them up in an equal time. As mentioned, each database is still isolated from a security perspective. They can't see each other's data, pages. It's strictly about sharing that compute resource. And again, just like standalone, for this provisioned, I can change this number. That same 2-minute thing would apply, that, hey, I want to change the maximum, minimum, the amount of vCores. I could increase it, I could decrease it. We'll go and spin up a new compute resource, which takes a couple of minutes. Once it's ready, switch the connections over, existing connections, we'll see a blip, the app will retry, it will connect, everyone is happy. So I can change that number just like we could before. But I want to stress the point. All of this complexity that I'm drawing on the board, because if you look at this, you're like, oh no, hyperscale is hyper complex. This is not your problem. This is all Microsoft's. It's their Xlog service. It's their pairs of page servers that they add. It's their multiple layers of cache. For you, this is actually the simplest configuration. You just tell it, hey, do I want serverless or provisioned, and the number of vCores. I don't even tell it an amount of data I want. I don't have to really do anything or manage anything from a provisioning of resource perspective or scaling things. It does it all for me. 10 gigabytes, up to 100 terabytes. I don't do anything different. And again, that's at time of recording. It absolutely could change. All I have to do is set what I want my compute to be and use the thing. But it can scale to these massive amounts, but it can also be a very reasonable amount, making it viable for lots of different workloads. And when we talk about viable for lots of different workloads, the brain is probably still looking at this architecture and saying like, well, yes, I could use it for smaller things, but it's probably going to be way more expensive than a general purpose or business critical of the others. And it isn't. One of the interesting things they've done here with Hyperscale, there is no licensing of the SQL Hyperscale. It's almost like using an open source from a licensing perspective. So if you compare the pricing, and you should go and do this for your requirements, compare the pricing of using the SQL Hyperscale to SQL General Purpose or Business Critical. Don't include, obviously, Azure Hybrid benefit if you're bringing a SQL license, because you don't need to bring a license for this one. You're just paying for the compute and the storage. So you're probably going to find it's actually cheaper than the other options out there, which is why things like the portal is now defaulting to Hyperscale, because I think they're really trying to get the idea across. This is not just for Hyperscale. Yes, it's capable of Hyperscale, massive amounts of performance, massive amounts of capacity, massive amounts of compute performance where I need it. It doesn't have to be. I can have a single box with one HA replica and a 10 gigabyte database. So it can be super reasonable as well. So what we've really done here is I've tried to stress the idea of the architecture so you understand what it is capable of and what it does. How I can have resiliency within the region, how I can have these replicas for analytical, for read workloads, how I can have the geo-replication, how I can co-locate. But you don't actually need to know any of it. As the customer, you just think about, hey, what's the compute I want? And then I write data to it. That's really it. And that is why I hate the name Hyperscale. I know for me, I absolutely thought this was only if I had some massive compute, massive storage capacity, or massive storage performance requirement. I would never even consider it in other more regular circumstances, which is just wrong. it's not what it's geared towards. It really is hyperscalable from small to very, very large. As small as 10 gigabytes is the storage I could pay for. I would urge you to look at the features, look at your requirements, and then ascertain which one is the best fit. Try and forget the word hyperscale. Maybe it should be Azure SQL vNext, Azure SQL++, Next Gen, Cloud, because it really was re-architected to be a born in the cloud database. But forget the naming, realize it's an option for many different types, and most SQL workloads actually should probably be running on Azure SQL Next Gen Hyperscale. I hope that was useful. And until next video, take care.